always have thought highly of the Northway Watershed Association, during Harry's leadership, and my esteem for the organization went up significantly when you guys decided to hire Judy. It showed you were really thinking very clearly. So, my wife and I have 2 children. Like all parents, we want our kids to grow up in a world that's safe and healthy and as productive as the world that we inherited from our grandparents. It's funny. I tend to not show things when I want people to listen to me. It's a really good thing. So, and today I want to explain to you why it is that the national academies of science everywhere in the world and all the major national and international scientific societies are saying that our future, and particularly our kids' future, is going to take a serious turn for the worse unless we take immediate action. But the first thing I want to do is tell you what I'm not going to say. Okay, so I'm not going to tell you what to believe. And I'm not going to tell you what's right or wrong. We all have our own value systems we use to determine that. What I am going to tell you is about objective scientific evidence that documents that we have a big problem. And in so doing, I'm going to ask that you listen to the skeptics, the real skeptics, the scientists. Objective skepticism is the heart of the scientific process. The oldest scientific society in the world, the Royal Society of London, has as its motto, don't take anybody's word for it. Now, our story really starts with this guy. Fourier was a contemporary of Thomas Jefferson's. He marched with Napoleon, served as Napoleon's governor of South Egypt for a while, and he was, in his spare time, a physicist studying heat. And Fourier and his colleagues reasoned that the planet should be much colder than it is, given how far away it is from the sun. And he postulated that there was a layer of heat-trapping gases in the atmosphere that warmed the planet further. And it turns out Fourier was right. And that is now a principle of physics that is known as the greenhouse effect. The Earth gets almost all of its energy from the sun, and most of the sun's rays pass through the atmosphere, striking the planet and warming it up. And just like anything else that warms up, a log in the fireplace or a frying pan on the stove, the Earth begins to radiate heat in the form of infrared radiation. Most of that energy escapes out into space. But because of this layer of heat-trapping gases, some of that energy is absorbed and then radiated back down to the planet. That warms the planet, and that's why the Earth has the temperature that it does. So Mars, which has a very thin atmosphere, a very weak greenhouse effect, is a very cold place. Whereas Venus, which has a very thick atmosphere and a very powerful greenhouse effect, has a surface temperature close to that of molten lead. And it's not because of the relative positions of the planets when compared to the sun, because Mercury, which of course is the closest planet to the sun, has a very thin atmosphere, a very weak greenhouse effect, and has a surface temperature well below that of Venus. Now, over the last 250 or 300 years, humans have been adding prodigious amounts of these heat-trapping gases to the atmosphere, mainly by burning coal, oil, and natural gas, and by chopping down forests. And this has had the effect of thickening that layer of heat-trapping gases. So now more of the energy that used to escape to outer space is absorbed and radiated back down to the planet, and that extra energy is what's forcing our climate to change. So Fourier postulates this in the 1820s, and in 1859, Irish physicist John Tyndall demonstrates in the laboratory that, in fact, there are components in the air that absorb infrared radiation. So this was a key proof of the mechanism underlying Fourier's ideas. And in 1896, and this is 20 years before Berkeley professor Alfred Wegener publishes the theory of continental drift, Swedish chemist Svante Arrhenius publishes the theory of global warming. And here's Arrhenius in the first page of his paper. And Arrhenius calculated what the temperature of the Earth would be if there was twice as much carbon dioxide in the atmosphere. And he got pretty close to the answer we have now. And the fact that he could do that with just a piece of paper and a pencil at a lot of time is what shows how fundamental the physical principles are underlying climate science. And now we are seeing with our own eyes and our own instruments that what Arrhenius and scientists after him postulated is coming to be true. The Earth is definitely warming up. I'll show you one of the 5 different temperature data sets that are available. The blue is the annual average temperature of the Earth, and the red is the 5-year moving average. You You may have heard that there has been no global warming in the last 15 years or 16 years or 18 years, whatever. That's a canard that was repeated in a presidential campaign by Senator Cruz, and it's a creation by starting in 1998, which is the hottest year in the past century, and then trying to draw the line to a La Nina year where the temperatures are lower because of natural variability. But if you just draw the line starting, say, in 2000, then you get this. And this doesn't mean there's runaway global warming. It means that 15 years is too short a time in which to assess the variability in this data set. And in fact, if you take a 15-year line segment, you can see how you could move it around and get it to tilt whichever way you want. But if you take a 30-year line segment, you can't do that, okay? Because then the underlying trend is the thing that you're seeing. Now, all of this is really nonsense now that when we add 2016, 15, and 16 to this graph, and we can see the effect of the El Nino. Another problem with just focusing on air temperature is that 90% of the extra energy that the greenhouse effect is capturing now is going into the ocean. And so the ocean temperature is changing. We can see it in all layers of the ocean. And what's really remarkable is about 50% of the increases happened since around 1990. And this is very consistent with the fact that about half of human carbon emissions over all of the industrial societies happened since 1980. So we have stomped on the gas pedal here just in the last few years. When you look at the temperature increase as a graphic around the planet, you can see the years going by here. You can see it's not uniform. There's more heating over land than over ocean. There's more heating in the interior of the continents than there is at the coastlines, which is a good thing for us, by the way. And there is more heating in the Arctic than there is in the temperate regions. And this Arctic amplification, this is something that was predicted in the 1970s by the National Academy of Science and by the Jason Committee of the Department of Defense, their high-level scientific advisory committee. Now, 180 years is not so long for a planet. How do we know this hasn't happened before? And that's a very good question, and scientists have been studying what we call proxies of temperature because we only have thermometer measurements going back to about 1880. And so what we do is look at things that we know vary with temperature, and we calibrate them with our current thermometer measurements. Then we go back in time and look at earlier temperature variations. And one of the best known of these proxies is tree rings, but there are many others. There are the sedimentary layer in the ocean and in large lakes. You can derive a pattern from that. Ancient coral heads, cave stalagmites. There are a lot of these different independent data sets. They all show that same temperature rise. One of the best proxies is ancient ice. You not only can get a temperature record from ancient ice using oxygen isotopes, but when ice forms, it captures tiny bubbles of atmosphere. And if you can get to ancient ice, you have samples of the ancient atmosphere. And so in the late 1990s, an international team was put together to go to Antarctica to drill because there the ice cap is 2 miles thick. And you can go back in time, not a couple hundred years or a couple thousand years or 10,000 years. You can go back in time 800,000 years. This data was published in 2003, and then the rest of it in 2006. I'll show it to you now. So in this graph, we have time we're going back in time from right to left. We have carbon dioxide on the vertical axis, and when we measure the tiny bubbles of atmosphere captured in the ancient ice, here is the record that we see. So there's definitely variability. But at no time is carbon dioxide concentrations above about 290 parts per million. Now, remember, we're squishing time on this scale, okay? So this red line is actually 300 years thick by the scale of the graph. So even though it looks like things are changing very, very fast, they're actually changing over thousands of years. Now, when we look at the oxygen isotope to get a temperature record from the ice, this is what we see. And in fact, temperature and carbon dioxide vary together, which is what you would expect from the physics of the greenhouse effect. But what's missing from this graph is modern industrial times. But I will add that now. So this is where carbon dioxide concentrations are today. So they are vastly above anything we've seen in the last 800,000 years. They are going up 200 times faster than any other time in this record. And if we do not have an immediate sustained effort to change the way we generate and use energy, then this is where we're going to be in just 35 years. Because carbon dioxide stays in the atmosphere for decades to centuries, when we put it up there, we're committing ourselves to future warming. So we have already committed ourselves to climate change, and we're beginning to see that happen. If we allow this to occur, we will be committing ourselves to such a massive change in temperature and related impacts, and we'll talk about this in just a second, that most scientific scientists are saying that it is unlikely that human civilization can survive in the form we know it today. It's a pretty drastic statement, but as we go through these changes, you'll get a sense of what people are talking about. Now, people also say, hey, wait a second, now humans, we're very, very adaptable creatures, and we have shown our capacity to manage things, and how come we can't manage this? And that's a good question to ask, and what we'll do is we can look just at the temperature change during the time that human civilization has been in existence. We'll say about 10,000 years, the first cities. And so when we do that, here's the temperature that we see. So there has been variation, but it's been only in the order of degree Fahrenheit, and it's gone up, then it's gone down, and this has been over thousands of years, except right here. And we can begin to see the impact of the changing of the atmosphere. If we allow carbon dioxide to continue to build up in the atmosphere the way we just showed, then this is where temperatures are going to go. There's a little debate about whether it might be 8 degrees Fahrenheit or 7 degrees Fahrenheit, but there's absolutely no debate about where this line is going. This is what's going to happen. It's just like if you wrap yourself in a blanket, you get warmer. If you turn the heat on under the kettle, the water gets warmer until you turn the heat off. Now, people have also said, hey, how do we know that, it's human activity, right? How do we know this isn't some natural phenomenon? That's another good question. Scientists have been studying that question for decades. And again, as I said, the patterns that we're seeing on the planet are patterns that we're predicting using the physics of the greenhouse effect. So that's one key thing. But if you look at the natural factors, the easiest way I've come to think about this is that the Earth is a very, very big thing. And because it's so big, there are very few things that can actually change its temperature. Imagine a friend of yours gives you an old clawfoot bathtub and puts it in your backyard and says, you should make a hot tub out of this. And he says, here, I've got a Bic lighter. You can use that to heat it up. You know, no, that's not going to do it. There's not enough power coming out of that lighter to change the temperature of the clawfoot bathtub. And in fact, there are very few things that have the power to change the temperature of the planet. One of the things that we know can do that is how far the planet is from the sun. And in fact, the Earth's orbit is not completely constant. It oscillates between being more elliptical and less elliptical. And as it oscillates, when it's more elliptical, the planet spends more time further away from the sun and ice accumulates on the planet. This is one of the drivers of the ice ages. But those variations happen on 10 to 100,000 year scales. So they can't explain temperature changes on decade scale. Now, another thing that can change the temperature of the Earth is if more energy starts coming out of the sun and hitting the planet. And in fact, the sun's output does vary, and it varies on the scale of decades. So that matches. But the problem is the amount of energy that changes is not enough to explain the temperature changes that we're seeing on the planet. And in fact, the output of the sun has been in decline over the last 20, 30 years, while temperatures of the planet are rising. So that doesn't explain it. If you put these natural features into a model of ocean temperature, this is from Tim Barnett's lab at UC San Diego, here you see the variation in ocean temperature driven by natural factors. Those big dips are actually volcanic eruptions. So volcanoes will erupt. Here's Mount Pinatubo in 1991 and put a lot of dust and particles into the atmosphere. So for a couple of years, it's like a parasol over the Earth, but gravity pulls them out, and then you're back to where you were before. Now if you put into the model the extra heat being captured by the carbon dioxide and other greenhouse gases in the atmosphere, the model says, well, this is the temperature of the ocean. So now you have a hypothesis, and we can go out and measure the temperature of the ocean. And when you measure the temperature of the ocean, this is what you see. And in fact, Barnett's group was able to reproduce different temperature gradients in the different ocean basins of the planet. So this is really the fundamental point here, that there is no way to explain what we are observing except for the impact of greenhouse gases. In addition, given what we know about greenhouse gases, there is no explanation for how it is that greenhouse gases are not causing this. Those are two different arguments. But it's because of those arguments that the US Supreme Court, our conservative Supreme Court, decided in 2007 that that we have to regulate, EPA had to regulate greenhouse gases as a threat to public health and safety pursuant to the Clean Air Act. When we then think about what's going to happen, I think John Holder, my PhD advisor, John Holder at Berkeley, has said that you think about climate as the envelope in which everything happens. All our natural systems and all of human enterprise. And when you change that envelope, you can change everything. So we are going to see changes in the availability of water. We've already got a little taste of that. We're going to see changes in the productivity of farms and forests and fisheries. This is going to challenge our ability to feed the people of the world. We're going to see increases in the prevalence of heat and humidity. We're going to see concentrations of air pollutants rise. Photochemical smog is a temperature-dependent process, and as air temperatures go up, we will get more ozone production. We're going to see changes in the geography of disease. The whole idea of tropical diseases, right? We now have the Aedes aegypti, the mosquito that will transmit dengue fever among mammals, is now well established in the United States as an example. Ticks are moving north. We're seeing damages from storms and droughts and wildfires. This is something California knows very well. Property loss from sea level rise and coastal erosion. This is going to be a huge problem in the Bay Area. And the distribution and abundance of species are going to be changed. We are wiping out massive amounts of natural capital. We don't even understand all the species that we are destroying. So what's going to happen around here? And in particular, I've been thinking about what's going to happen to the ecosystems of our region. Now, some people might say, well, okay, I like birds, I like walking by the bay, but given the threat that I just described, shouldn't we be focused on our infrastructure, our roads, our bridges, our hospitals, our pipelines? And what I would say is, sure, we have to focus on those things, but we have to recognize that our ecosystems are infrastructure as well. They are our natural infrastructure. We didn't build them. They self-repair. They provide inputs to our economy that we depend upon. And that's going to be changing. So we look at the mountains, right? Now, some people, when I talk to young audiences, it's like, skiing and snowboarding is what they think about here. I look at the snow-covered Sierras and I see California's original water towers. So our water system is designed, as I think most of you know, around that snowpack. It sits there and accumulates in the winter, and then we capture the meltwater in the spring. We use it in the summer and the fall when it doesn't rain in our Mediterranean climate. But that is going to change. Okay? We are already seeing the snow level moving up, and so we're going to get more winter rain, less winter snow. The rain, of course, doesn't stay up in the mountains all winter. It immediately comes down. We'll see more winter flooding, and we'll have less water in the spring and the summer. And in fact, the whole problem that we saw last year with Oroville Reservoir was driven by a rain event on the snowpack. This is what generated the massive flow of water that couldn't be contained in the reservoir. Our mountain ecosystems are actually our water treatment systems, right? They store and clean this water, deliver it to us in these very convenient things called rivers. The Tuolumne Meadows is, it's a international tourist destination, but it is San Francisco's water treatment plant. And for the other folks around the bay who get water from the SFPUC, our coastal ecosystems. And San Pablo Bay, of course, is full of these coastal wetlands that
attenuate waves, reduce erosion, they help clean the water, and they provide incredible habitat for birds and fish. The bay itself is part of our wastewater system, right? We discharge, as a region, 500 million gallons of wastewater a day in the San Francisco Bay. And the bay just takes care of it for us while continuing to act as a world-class harbor and producing over $250 million a year of commodities that we can use directly. In addition, the physical beauty of our natural environment is part of our economy and our quality of life. The fact that there are whales in the Gulf of the Farallones is valuable to people, even people who get so motion sick, they would never dream of going out there and looking at them themselves. Our natural lands, besides capturing and storing water, are part of what makes our region an international tourist destination. But all of these, what scientists call ecosystem services, all of these things that we get are going to be stressed as climate changes, and that's going to impact our economy and our way of life. We, of course, are already seeing getting a glimpse of what sea level rise looks like. If you haven't been to the California King Tides website, you can go there and see photographs. Right? The king tides happen twice a year when the moon and the sun are aligned. You get the maximum pull on the waters of the planet. They are just a preview of what regular high tide is going to look like in 30 or 40 years. These are projections for sea level rise that I'll show you from a National Academy of Sciences study that Senator Feinstein had performed for the western coast of North America. And all of the data that has come out since 2012 is moving that blue line towards the red line, not towards the white line. And in fact, the recent update from the Ocean Protection Council includes a scenario they call H++. And under this scenario, sea level rises 10 feet by 2100. Now, the reason it's there is not because that is necessarily likely, but it is because the more we learn about how ice sheets fall apart, the more we're realizing that there is an absolute physical process that could result in an incredible acceleration in the decline, particularly of the western Antarctic ice sheet. And what's fascinating for us here is that we get more of the sea level rise from the western end, from Antarctica than the east coast of the US does. You'll also notice that none of these lines are straight, right? They are curves. And sea level rise is going to be going up faster in 2100 than it is now, because it takes so long for the great ice sheets to change as we put more energy into the planet. So these are actually big, if you run it out to like the 25th century, they're big sigmoidal curves, right? And it'll slow down towards the end, but by that time the waters of the planet could be hundreds of feet higher. So we're seeing these effects. You know, this one is one I'm sure that all of you guys are very familiar with. And in fact, Highway 37 is like the cauldron for adaptation planning, you know, in the region. It's one of them. And I'm sure you all know more than I do about the topic, but it's clearly a piece of infrastructure that's going to have to change very quickly. We have so many assets at risk. Here's just a picture of the South Bay. The light color is 16 inches of sea level rise. The red color is 55 inches of sea level rise. And you can see a number of these campuses that are at risk. The impacts of sea level rise are because they exacerbate flooding. And so when we get storm surges here in the Bay Area, and they're nothing like the storm surges they get in the Atlantic coast after the hurricanes, but I'll show you one here. So this is the Hayward shoreline south of Orloma, and then I'll show you the same shoreline during a major storm event that had a big westerly wind. And so you can see that the levee has almost disappeared. Now put 2 feet of sea level rise on top of that, and you realize that the bay would be pouring over that levee. And the next thing actually here in Hayward is the railroad track. It carries so much of the freight from the Port of Oakland. Coastal erosion is a big issue. For those of you who are familiar with a part of the California coast, you probably noticed this year it looks really different than it did a year ago. And that's because our big El Nino year, which didn't actually come with as much rainfall as we thought, did come with a huge wave, change in the wave patterns. And we had one of the most powerful winters that we'd ever seen. And we have had more coastal erosion on the coast than the USGS is monitoring this, and we've seen more erosion than ever. And a lot of people who have a favorite beach have probably noticed on the coast that there's a lot less of it than there used to be. Another impact we're going to have to deal with here in the Bay Area is that warm air holds more water. And so when it rains, there's more rainfall that can come down, and we're going to see more flooding. Like this one in San Anselmo, we're going to have these flood impacts because not only have we been unable or unwilling as a society to maintain our flood protection infrastructure, and Highway Proposition 13 had a huge impact on the capacity of probably many of your agencies, I know, to deal with this. But we're also they were never designed for the kinds of storms that we're going to see. Here's a picture from. I'll show you a picture from San Francisco Creek, which is the boundary between Santa Clara and San Mateo counties. This was in Christmas 2012. This is the finding the city of East Palo Alto made to the state in order to qualify for emergency aid. You can see the crack in the levee here, and we almost lost it. Water was boiling under this levee and damaged one house. If this levee had failed, a large part of East Palo Alto would have looked like the Ninth Ward during Hurricane Katrina, with standing water against the sides of houses. Arid areas are going to be getting more arid. One of the prime locations, of course, is the Colorado River Basin. Not only is this because of change in circulation patterns, but because even if it rains the same amount, it's going to be warmer, and so we're going to get more evaporation. This is a huge political problem because, as many of you might know, the Colorado Compact was negotiated 100 years ago between the states, and it was based on flows between 1900 and 1920, which is the highest flows in the Colorado River in the last couple hundred years. And you have a last in, first out deal here for the states. So the first cuts, which happen when Lake Mead reaches 1,075 feet above sea level, the first cuts go to Arizona and a little bit to Nevada, not to California. And that's not going to be popular. They are actually releasing water from Lake Powell to keep Lake Mead up above that level while they try and negotiate what they're going to do. To me, the most serious problem we face because of climate change, that is, it's not actually in the North Bay itself, but it will affect us all. And it is the political cascades of events that are going to occur because people are going to be on the move, because there's not going to be enough water and food for people. The ex-director of the CIA, R. James Woolsey, and colleagues did a study in 2007 they called The Age of Consequences. This is what they concluded. Now, we all have our own kind of sensibility about what is profound. And I've been using this quote for years, and I've been trying to find what is really profoundly disquieting to me, a picture that sums it up. This is profoundly disquieting to me. These people are on the move from a war-torn region. Part of the reason there was a war is because there was a drought, the worst drought Syria had ever seen, and it drove 1 million people off the land and into the cities where the Assad government was either unwilling or unable to help them. Imagine what it's going to look like when there are millions of people on the move. The economy, you often hear this statement, like this was from Marco Rubio, I remember, we can't destroy the economy to save the environment. The economists are saying that is completely the cart before the horse, right? This is what they're saying, okay? And study after study has shown this basic idea where we invest now or we pay more later. Here's what Sir Nicholas Stern said, but he just increased the higher end of his high bill in the future to 50 times the event. And what's interesting here is 1% of global gross domestic product just so happens to be approximately the same amount of money we spend as a society
to move from a society based on chamber pots to a society that has sewers and indoor plumbing. And most people think that was a pretty good investment. And we're going to be making investments anyway. And the trick is, as Robin was mentioning earlier, investing in things that we know will be resilient in the future. I kind of think about the words of that famous environmental philosopher, Wayne Gretzky. So Wayne Gretzky was asked, "Why are you such a good hockey player?" And he said, "It's because I skate to where the puck is going to be, not to where the puck is." And that's what we're going to have to do as a society. Now we have a tremendous amount of technological options available to us. Just wind power is incredibly, there's enough wind over the world to provide all of our electricity. It's not to say that we should do it only with wind. But these technologies now have dropped in price in a remarkable way, and that's not even including the external costs associated with burning fossil fuels like health impacts. Solar power has also dropped in price, and as a result, this is what's going on in PG&E service area. PG&E has more rooftop solar than any other utility in the country. And despite what happened yesterday, we have all of the nations of the world recognizing this fundamental problem. And I think that what the president did yesterday is going to go down in history as one of the most short-sighted and decisions driven by ideological nonsense. But I don't think it's going to actually have a very big impact. We'll see. I mean, I think that the stuff he's been doing with the Clean Power Plan, I mean, that's going to have some impact, but already today, our governor, I don't know if you guys heard this, but our governor has announced a new association that currently has New York and the state of Washington in it, and these three states who expect to be joined by others have committed to meeting their own Paris goals. And we're going to become a pariah and a laughing stock, and no one's going to want to collaborate with us on other things, and I won't go on. But the good news is that we are actually, I hope, beginning to see emissions plateau. Because remember, the commitments made in Paris are important, but they are just a minor down payment on what we have to do. Okay, we have to turn this curve over and send it down to zero by the middle of the second half of this century, and actually send it negative. We have to be pulling carbon out of the atmosphere if we're going to have a good chance of keeping global temperature increases to 2 degrees centigrade. I think John McCain said it really well. Okay? Unfortunately, I think he's failing the test he set up for himself, but maybe we'll give him an extra credit round and see if he can come back. This is a moral quandary because of the intergenerational nature of the facts. I don't know what we're going to say to the kids born today in Nevada when they turn to us in 20 years. And they say, are they going to say, how could you do so little when you knew so much? Are we going to be reduced to begging for our children's forgiveness? Much better, I say, they put their arms around us and they say, thank you for taking action when you did, because otherwise I know things would be even more challenging for me. Remember that the climate change that's coming in the next 30 years has already been decided by the emissions in the atmosphere. The question is whether we take action today, that 40, 50, 60 years from now, things are different. That's the question of our day. And one way or another, it can be answered in the next 10 years. Apollo astronaut Wesley Schweickart said, we're not passengers on spaceship Earth, we're the crew. We're not residents of the planet, we're citizens. And the difference in both cases is responsibility. Thank you so much for your attention.